Welcome back. Today we're looking at differences of one variable, two variables, and multiple variables. This is related to the idea of different kinds of analytics: descriptive, predictive, and prescriptive. And so we're starting off here in this area in today's discussion. Descriptive analytics, in which something has already happened. Here's another way of thinking about those different levels of analytics or categories: past, present, or future. In the past, descriptive, what happened, and that's where we're at in thinking about what happened from the standpoint of differences. So we're going to first look at one variable and look at both the idea of hypothesis testing and confidence intervals for one variable. Confidence intervals: when we take a sample of data and calculate statistics such as means and standard deviation and so forth, from that sample we know that mean and that standard deviation is very unlikely to be the true mean of that population. We've taken a sample, yes, and from that sample we're computing statistics. But we know that that's not exactly the true answer, and so we need a way of understanding the uncertainty associated with our statistics. In this case, with the mean. And so this is showing some population of data, and from that population of data, we've constructed a mean and a standard deviation. This is a way that I think is a very convenient way of thinking about what we're faced with in describing our confidence interval results. In this case, 25 samples of size 100 were taken from a data set. And this line here, this is the true but unknown population mean from that data set in which we've taken samples. And each of these lines represents constructing a confidence interval, with the dot being the mean, and then these two pieces here on either side representing our confidence interval, the plus and minus part to the mean. And notice that many of these overlap the true population mean. Some overlap towards the center. Some overlap with the mean to the left of the true, our statistic sample mean, to the left of the true population mean. Some to the right. Some just barely on the edge. Some right there, almost exactly on it. But then some are not going to cross over that. So just a method of constructing this confidence interval tells us that if we constructed, say, 100 confidence intervals, and we constructed them in a way that we were looking for a 95% confidence interval, then 95 out of the 100 would cross over the true mean in some way, and 5 wouldn't. The problem is we don't know which 5. We've got one of those, say 100, but we don't know which, whether that particular one is one that crosses over the population mean or not. And so when we construct this confidence interval, we really construct every kind of confidence interval in sort of this way, in that we have some point estimate, such as a mean. And then here's our plus or minus for our confidence interval on either side of that estimate. And this is always some confidence level multiplier. So do we want to have a 95% confidence interval, or 99%, or whatever? And then the standard error of that statistic. And when that's constructed, this is what we can say about it. We can say that, for example, 95%. We can say we're 95% confident that the true but unknown population parameter is between that lower and upper confidence interval limit. So if we constructed this and we get one of these, we don't know which one, and say there were 100 of them, then we would be saying we're 95% confident that our one particular confidence interval overlaps that, and that gives us some basis of constructing this confidence interval. Just the way that we're constructing this gives us the ability to state our confidence interval in this fashion. So how do we find a confidence interval for the mean in JUMP? Well, we talked at one point about this platform called analyzed distribution. Well, in analyzed distribution, for this continuous data, we get both a histogram and summary statistics. As it turns out, those summary statistics are just automatically going to give us the upper and lower confidence intervals. These two endpoints, they give us the overall mean, and then that lower confidence interval, upper confidence interval points for constructing the confidence interval for the mean. So using the equity data that's in the JUMP sample data set, if we looked at the variable for loan, then we would see this result, and we would see this 95% confidence interval. And we're not limited to a 95%. We can change that confidence interval level to something different than 95 if we desire. And this shows us the formula for how that is being estimated. Let's go now to hypothesis testing. Every hypothesis test, I think, has these elements. There's a null and an alternate hypothesis. The null is not what you're proving. We always either reject the null and accept the alternate, or we fail to reject the null. The null hypothesis is always a hypothesis of no difference. That is, if we had an hypothesis where we want to look at something equal or not equal, the equal part would be in the null and the alternate would be the not equal part. But if we had a one-sided, in which, say, the null was a less than or equal to, so the equal part here in the null, then the alternate h sub a would be a greater than. And if we had a one-sided in which the null was a greater than or equal to, then the alternate would be a less than or equal to. Well, to test that, we need a test statistic, and it depends on our question and the data. We construct this test statistic. We compare it against a reference distribution, and then this gives us the probability of whether, if we reject the null and accept the alternate, it gives us what's called this p-value. And we compare that against some predetermined threshold, such as say 0.05, and if the p-value associated with our test statistic gives us a p-value of say less than 0.05, then we'll reject the null and accept the alternate. So we end up with really these two alternatives. We reject the null and accept the alternate, recognizing that we have this probability of being incorrect, what's called a type 1 error, or we can fail to reject the null. So here we're seeing a two-tailed test, and so that we compute the test statistic, but then what's called the rejection region. If our benchmark is going to be say 0.05, is divided equally on either end here. If we had a large sample mean, then we'd be using what's called a z-test statistic, but the form of our test statistic is this. very similar for a t-test statistic. From that same analyzed distribution result, there's a red triangle that allows us to state our hypothesized mean, and then JUMP will generate the associated statistics and p-values for that. So again, with the lone data, if we were to say a hypothesized mean of 19,000, and if I wanted to test whether our null would be that the mean is equal to 19,000, our alternate would be H sub A that the mean is not equal to 19,000, and that would be a two-tailed test, and we would be looking at this value, and for this we would reject the null and accept the alternate that the mean isn't 19,000, and here's the probability of that type 1 error, that p-value. So another example here based on insurance profits. Suppose a manager wanted to see how their sales rep was doing. A sample of 30 policies wants us to construct a 95% confidence interval for the mean profit of the policies sold. Here's our original data. From that data set, we just do analyze distribution. Then we're going to automatically get this result here, the histogram, and the summary statistics, of which we're given that 95% confidence interval. 95% confident the true population mean is in the interval 942 to 1935. What if we want to know if there's any evidence that the mean profit is less than 1,500? Well, we're going to specify this hypothesized mean. In this case, it's going to be a one-tailed test. And because it's a one-tailed test, remember the no difference part goes in the null. So the null is for hypothesizing the mean is greater than or equal to 1,500, alternate less than 1,500. We would use this particular value, result of our p-value for making this decision. Because this p-value is very large, more than 0.05, we would have a fail to reject on the null. And that's it. Thanks. See you next time.